Right, gents, today's topics. We're going to briefly look at measurement of angles in both radians and degrees. Largely a revision of what should have come before in some other course, really. Pythagoras theorem and trigonometry for right angle triangles. And then sine and cosine rules, and finding the area so you can solve any triangle that isn't necessarily a right angle triangle. And then finishing up, we'll look at wave functions, so the function of a sine wave in terms of its frequency, period, and phase shift, and so on. And all this is useful work largely in the electrical field, but also oscillating systems come into mechanics, the mechanical side of things as well. So you're going to come across them in science in semester 2. So, angles in degrees and radians. We can measure angles in either of those, and a lot of the time one of the key things you need to be aware of with your calculator in the exam and when you're doing problems is whether you need to have your calculator set up in radians mode or degrees mode. If you see pi at all, you're going to be talking about angles in radians, because that's pi is related to that. If we go in degrees, in engineering we always talk about angles in terms of positive being in an anti-clockwise direction. And that's true whether we're in degrees or radians, but we talk about positive angles around the circle, and there's 360 degrees in a full circle. There's 2 pi radians in a full circle. So an angle over here is pi radians. 90 degrees is pi over 2. Three pi over 2, or 1.5 pi is 270 degrees. Okay? However, having said we use positive angles, in the electrical field certainly, if we're talking about an angle down here somewhere, we're more likely to call it minus 45 degrees. So we will work with positive and negative angles in this range here between 90 and minus 90 degrees when we're doing electrical work. Okay, occasionally you'll get angles over here as well in these areas between positive 90 and 180, negative 90 and negative 180 as well, but not that often. Okay, it fits in well with what we'll talk about a little bit later, but leading and lagging sine waves, as one's got a lead and one's got a positive angle between 0 and 90 degrees, and a lagging one's got a negative angle, usually between 0 and 90 degrees negative. Okay, so here we could be talking about minus pi over 2 for 90 degrees downwards, as opposed to 3 pi over 2 radians. Okay? You're reasonably happy with that so far, yeah? So, depending on what the flavour of the question, we may need to be talking about angles in either degrees or radians. We also might need to convert from one to the other. So, a problem. Convert to radians. 125 degrees. How might we do that? In 180 degrees, there are pi radians. So if we divide that by 180, we got how many degrees there are for, how many radians there are for 1 degree. If we then multiply that by the number of degrees we got, yeah, we should end up with how many radians it is. So if you plug that into your calculator, you should get the correct answer. Might be helpful to have a bracket over that, or use the fraction facility on your calculator too. 3.18, and on my answer I got an extra 2 on the end, but that's what you decide to round it to. 4 significant figures. Because as soon as you evaluate pi in your formula, you're going to fill the whole calculator up with decimal places, aren't you? Yep. B, 69 degrees, 47 minutes to radians. 4 minutes. How many minutes are there in a degree? Anybody know? Yeah, there's 60. So let's make that note. 60 minutes in 1 degree. So how are we going to do this? We know we've got to do equals pi over 180 degrees. Got to do that bit. We're going to multiply it by 69 degrees and 47 sixtieths for the minutes. Yeah. We should get an answer. What we got? Come on, get your calculator out and do it. You're going to need to do it in the exam. You can do, if you do the shift on your fraction button, you can do a mixed number with a 69 in front of it and then the fraction after. 1.218? Correct. If you don't put the degree symbol, then radians are assumed. But I like to see someone just put rad after it so you confirm that they are radians. Alright, everybody happy with that? Can I move on? Yeah? No dissenting voices. So, convert those to degrees and minutes. 0.749 radians to degrees and minutes. How are we going to do that? It's a similar calculation. Times that. Answer is? Okay, you got 42.92, but we want it in degrees and minutes. So let me get my calculator out. That one's got no difference. Put that 0.92 into not quite, not 92 over 60. It's 0.92 of 1 degree. Yeah? 1 degree equals 60 minutes. So surely that's 0.92 times 60 to get the degrees. Yeah? Alright. So that equals 42 and 0.92 times 60 minutes. Yeah. .42 degrees and 55.2 minutes. That's what I make it. Yeah. Yeah. That will convert.
Did you have to do that?
You don't have to do anything, but I'm not going to likely to be asking you to convert between radians degrees specifically, but you may need to. So you need to know how to do it one way or the other. Yes, there is a button. Does that give the same answer as we got, more or less?
Yeah.
Yeah, it'll give you the seconds on the end as well. Yeah. All right. So 42 degrees, 55.2 minutes. So we can have our angle measurements in a decimal fraction degrees, or we can convert the decimal part of it to minutes. That's appropriate. Okay. The second one, B, is convert 3 pi over 4 radians to degrees and minutes. Yeah, so same method. We're going to do 180 over pi times 3 pi over 4. Everyone else agree with 135 degrees and no minutes? There's a button on your calculator, as Caleb has pointed out. It's got degrees, minutes, seconds on it, like that, and it will convert your, it's next to the minus button on mine, convert between the fractional and the degrees and or the number with the decimal place and the degrees, minutes and seconds. So this one at 42.492, if you hit that button, after you've done the calculation, look like it, you've got to do the calculation, it will convert it. Yeah, 42 degrees, 54 minutes, and 52.34 seconds, that first one, to be precise. So that button will do that conversion for you if you want it to, if you need it in degrees, minutes and seconds. Okay? That's the button with that on it. It's got a little circle, 1 speech mark, 2 speech marks, degrees, seconds, minutes. If you type in that calculation and press equals, and then hit that button, it'll convert it to degrees, seconds, minutes and seconds. Right, moving on just a little further. With angles in radians, it's often more useful not to evaluate pi as the following demonstrates. Okay, express in radians in terms of pi. So we're going to do A, 150 degrees to radians, in terms of pi. So our conversion is, how do we do that? From, sorry? Pi of 180 times 150. Do that on your calculator. If you've got your calculator set up how mine is, I'll give you an answer like this. And that's what it's looking for. 5/6 pi radians. My calculator says it's in what's called math mode. I don't know whether that's the key to this, but you can, if you've got a fractional result, push the S to D button, and then you'll get it like that. So it depends on how you got your calculator set up, surds or decimals, that's what that is, and that button switches backwards and forwards between 2.618 to 4 decimal places, or 5/6 pi. And it's quite useful, particularly in electrical. When you go on to you do further calculations, you often find that the pi's cancel each other out anyway, and you don't get the issue. And like I keep saying, it's best if you don't evaluate pi until right at the end of your calculation, because all it does is encourage you to round off and create an error which might not be necessary anyway. Okay, so your calculator will automatically, in a lot of cases, give you a result as a fractional number of pi, 5/6 pi. It might be a top-heavy fraction, 6/5 pi in some cases, 10/3 pi or something, but that's easier to leave it like that in many cases than have this decimal that you could write out incorrectly or type into your calculator wrong. Okay, so just do the other two and see if you can get those results in a multiple of pi. So to sum up there, it's often worthwhile to leave your radian angles as a multiple, or even if it's a fractional multiple, a multiple of pi, or in terms of pi would be the mathematical way of saying that. Alright, so we're going to do now, let's move on again, if everybody's happy. We're going to do a little bit of revision of something that you may well have done at school, in BTEC, or might have been years ago, but Pythagoras theorem. In any right angle triangle, square on the hypotenuse. Hypotenuse is the side opposite the right angle. Another way is to say that's the longest side of the three. Okay, is equal to the sum of the squares on the other two sides. Usually, mathematically label up a triangle with the angles on the corners having capital letters A, B, and C, but other letters can be used. And then you use the lowercase letter for the side opposite that angle. So we've got a capital A here, and the side opposite is a lowercase a. There's a capital C, and the opposite side is a lowercase c, and a capital B against the right angle, and the opposite side is a lowercase b. And we got Pythagoras theorem there. It's a little bit small on the screen, but it says that the square on the hypotenuse, i.e. lowercase b squared, is equal to a squared plus b squared. Well spotted. C squared. Yeah. I'd normally label the right angle A actually, but if that was me, but it doesn't really matter as long as you read it, and I didn't. Okay. So find the length of the side EF, or find D. What it's saying here then is this one. So according to the labelling of that triangle, E squared, the hypotenuse, is equal to D squared plus F squared. We want to find D, so we need to do a bit of algebra to rearrange that. Have a go at that. A couple of minutes, should be done easy. Right, what's the first step in rearranging that then? Take F squared on the other side. So I'm going to start off by being D squared. Now I'm going to take E squared minus F squared. So subtract F squared both sides is what I've done, or what you've told me I need to do. And next, would you do that yet? Got D squared equals at the moment. Square root at the end. Okay. Nothing particularly wrong with that, I suppose. But I do square root both sides. So we'd end up with D is equal to the square root of all of that. Then put the numbers in, just preference. E is 13 minus F is 5. So that's the square root of. I just do that in one go in the calculator. Sorry, 12, yeah. Like the 3, 4, 5 triangle, that's one that's got equal and integer sides. Classic. 5, 12, 13. And that's got some units into centimetres. Okay? I wasn't expecting really to spend too much time on this, to be honest. Okay? So, if I give you pretty much, I'm quite confident that, and are you confident, if you had a triangle, you knew two of the sides, and that's a right angle triangle, you could use Pythagoras' theorem to find the unknown side. Yep, everybody happy with that? So, trigonometry for right angle triangles. Okay, on this page, because we're doing maths, I'm including the inverse ratios as well. In engineering, in the course we're doing, you aren't going to come across secant, cosecant and cotangent a great deal of times, but they can be useful in some, yeah, could do, yeah, okay, but they're in here for completeness, but you won't come across them in my science in semester 2, for instance, and I don't have anywhere that I use them in electrical principles at level 5, but you could well come in across them next year in the advanced maths module if you're doing that. Okay, so the three ratios are the sine of an angle theta. This angle here is the opposite side divided by the hypotenuse. So how it's labelled, sine of it is the opposite b over the hypotenuse c. Cosine is the adjacent side divided by the hypotenuse. So the adjacent side is a and the hypotenuse c. And then the tangent of an angle is the opposite side b divided by the adjacent a. So they're the three main ratios: sine, opposite hypotenuse; cosine, adjacent hypotenuse; tangent, opposite adjacent. SOHCAHTOA, or when I was at school they taught us some officers have curly auburn hair till old age. There are various ones. I mean, I still remember the resistor colour code one I was taught, that as Billy Brown revives on your gin but prefers good whiskey. So if you have something that helps you to remember the right angle triangle ratios, then use it. Okay. Then over this side we've got secant, sometimes often shortened to sec, and it's just the sine ratio turned the other way up, so it's hypotenuse over adjacent. Cosecant is hypotenuse over the opposite side, and cotangent is the adjacent over the opposite side. So they are just the ratios flipped up the other way. Please do not confuse this one with sine to the minus 1 of an angle, or this one with cos to the minus 1 of an angle, or this one with tan to the minus 1 of an angle. They are not the same thing. Those functions on your calculator are saying, what is the angle that has this tangent? It's taken the ratio and turning it into an angle in either radians or degrees. Okay, no to the power minus 1 on a number means the reciprocal of, but all it means with these buttons on your calculator is they are the inverse function of getting a sine from a fraction. They turn it back into the angle in degrees or radians. Okay? These are actually the ratio turned up the other way. They're called the reciprocal ratios, according to Mr. Bird. Everybody happy with that? Yeah. What that means is we can use them to find the lengths of sides and unknown angles in a triangle. What's the quickest way to find out the angle P in that triangle?
Choose 90, isn't it? Choose 38. Yes, yeah. And 90, 38.
Yeah, that. So the two angles are there. Add them together and take them off 180. Which is 90 and 38 is 128. So we're talking about 230, 52 degrees. Am I right? The question didn't ask you to find that, but we don't need to fiddle around with a ratio trying to find that angle. Just the remainder of 180 degrees. Find the lengths PQ. So how do we find the length PQ? This one, using the ratios. We've got this angle here. We've been given the adjacent side, and we want to know the opposite side to that angle. What ratio do we want? Tan of R is equal to PQ in the way they labelled this over QR. We're looking to find the side PQ. So what we got to do to this to get it in the right order? PQ equals QR tan R equals, and the side QR is 7.5 times the tan of 38 degrees, wasn't it? Yeah. Okay. When you write formula out, you can put a dot between things that are multiplied together. When you put the numbers in, you need to go back to putting the multiplication symbol between. Okay? Otherwise things get confusing and get muddled up between the dots that are multiplies and the dots that are decimal places. Alright? So the answer to that is? And what's missing? Yeah, the length of the side, centimetres. And the other part of the question, using the ratio, find PR. So we're looking to find the length of the hypotenuse here, this side. Well, you've been given the angle in degrees, so what do you think? I thought it sounded a bit short. I was waiting to see whether there was a mistake. You got your calculator in radians, Paul? Yeah. Well spotted. Okay, it's important. 5.86, everybody agree? I thought it seemed short, but I was waiting.
You're not the first person to say that,
Paul, pack it in. Right, what ratio could we use to find this side PQ here, PR here? What ratio would you use? If to use sin or sine, Paul, what sides do we need to use? Opposite, right? That side, and the hypotenuse that side. Yes, you do. You just calculated it. But my argument would be, use the side you've been given, because you may well have rounded that figure. You haven't rounded that 7.5. So I would use cosine as opposite over hypotenuse. Because you've been, cosine is adjacent, over hypotenuse. Because the adjacent is the given side. Sorry, Jake, you're looking puzzled. All I'm saying is, yes, you could use the sine of the angle, but you'd be using a calculated value that you might well have rounded, and you don't need to, because you can use the cosine and this 7.5 again. You've got an angle you've been given, and you've got a side you've been given. And therefore, you aren't going to be compounding errors. Alright? So yes, you could do it that way, and your answer could well be quite close, but in some cases, may not be. So the idea here is don't introduce errors that you don't need to introduce. So we're going to go down the road of using cosine of the angle, R, is equal to the side QR over the side PR. And we want to find PR. So what we got to do with that formula, get it into PR equals something. What do I need to do to rearrange that so it's in terms of PR?
PR equals QR on R.
Tell me step by step how you got to that, Paul. Do it one step at a time. How do I get PR over to the left-hand side? How could I make PR cancel out here? Yeah, multiply by PR. Because then that would become QR PR over that, and they would cancel out. Yeah, so we've got to go like this. PR cos R is equal to side QR. Alright? That's the first step. Multiply by the side PR. Next step is we need to get cos R over this side. How do we do that? Divide by cos of R. That leaves us with PR is equal to QR over cos R. That is the 7.5 centimetres over the cosine of 38 degrees with the calculator in radians, gentlemen. Answer? Sorry? 9.518 to 4 significant figures. Yeah, centimetres. Nine point how many?
Oh no. No, we used to add, yeah, sorry, yeah.
7.86.
Okay, so we could use Pythagoras' theorem here to check our previous answers are in the right ballpark. So always worthwhile having a method to check. Let's have a look at a worded problem around this. A surveyor measures the angle of elevation at the top of a perpendicular building as 19 degrees. So here's our building. Here's a distance away. Yeah. And he measures this angle in here as 19 degrees. Right? He then moves 120 meters closer to the building and finds the angle now, put it in a different colour, from that position is 47 degrees. Determine the height of the building. Does anyone see how to do that? Yeah, you can minus. What angle would that give me, Caleb? That'd be that one. Yeah. We haven't done non-right angle triangles yet, so what could we do here? We're kind of combining some of the other techniques that we've used earlier here. This problem needs you to do some. We're looking to find this, aren't we? We want to know h in there. What could we express this distance as? Yeah. If we call that distance x, an unknown, our common unknown variable, what would we say this distance is? Yeah. So, we've got an angle here, we want to find that, and we've got an expression for that side. So what ratio would we use involving that 19 degrees, that h, and that x plus 120? What ratio involves the opposite side and the adjacent side? Yeah, so we can write tan of 19 degrees is equal to h over h plus 120. Okay? X plus 120. Then if we can rearrange that for h. So how do I rearrange that for h? Might help if you think of that being in brackets. Because that's just a number. It's an unknown number plus a constant. Yeah, so we can write this as h is equal to tan 19 degrees times x plus 120. Okay, so we've got one expression for h now, but we've got an unknown variable of x in it. What about this angle, this triangle, in terms of the angle we know, the distance h and the unknown distance x? How could we express that using the ratios? Which ratio would we use again? We know we got if we want to involve the opposite side h and that unknown x, what ratio would we use? I'm going to shift that over a little bit. We got opposite and adjacent. So over here also tan of 47 degrees now is equal to h over x. So we've got two formulas involving the two variables now. Okay. Rearrange that one for h. What? You could do, but we ain't covered that yet, Dominic. Right? So we're doing it a different way. Okay? But we're using some techniques that we've already used. We're looking for two equations, and then we're going to solve it by getting rid of one of the variables. If we rearrange that for x, what would that be? H is equal to. Yeah. Tan 47 degrees times x. Okay. Right. Now what we've got are two formulae that express two different formulas that express x. That express h. Tan 19 degrees times x plus 120 is equal to h, and tan 47 times x is equal to h. H and h are the same thing, they're equal. So what we can do is write down now, because tan 19 degrees times that is equal to h, and tan 47 times x is equal to h, we can say those two formulae are equal to each other. Does everybody see that? Because h is the same thing all the time. So what we can do is write tan 19 degrees x plus 120 equals tan 47 degrees times x. What have we done by doing that? H has gone. Yep. So we've only got one unknown now. What do we need to do now? Need to get x on its own. How do we go about doing that then? Divide this size by tan 47. Yeah, you could do that. First thing really would be to get both the x's in the same place, wouldn't it? Divide through by x plus 120. Divide this side through by x. What are your options? What? You need them both the same side. You need to get one lot of x. How are you going to do it? If you do what? Did you say, Jake? Yeah. So you've got tan 19 equals tan 47 over So you're going to do tan 19 over tan 47 is equal to x over x plus 120. The x's don't cancel out. How else could I write that? I could write it as x over x, which is 1, plus x over 120. This actually isn't the best way for you to go with this. Okay? I'm going your way to try and show you, and then I'm going to show you the way I would go from the start. Okay? It's not always this good example of us not always easy to know where to start with these rearranging formulae issue, but we have been over quite a bit of it. The best way to start with this, I'm going to repeat the page. I'm going to leave that on for the benefit of the video. Go down. Get rid of that. Your best bet here is to get rid of them brackets. Multiply them brackets out. So we'd have tan 19 degrees times x plus 120 of tan 19 degrees is equal to tan 47 degrees times x. This bit is just a number. Yeah. That bit involves x. So if we leave that bit that side, how can we get the bit involving x over to the other side? How's it attached to this side? Got a plus in front of it, isn't it? You've got to subtract it, yeah? So we got 120 tan 19 degrees is equal to tan 47 degrees times x minus tan 19 degrees times x. What can we do over this side now? Looking at these two, if we divide by tan 47, we'll cancel it out there, but we'll have this as tan 19 times x over tan 47. What's common to both those two? X. So what can we do with common factors? What can we do with common factors? Remember, between these, there's a multiply. That's what that dot is in there. So this is tan 47 times x. That's minus tan 19 times x. What can we do with common factors from previous weeks? What do we do when we factorise? No? Take them outside a pair of brackets. So we can go 120 tan 19 degrees is equal to x times tan 47 degrees minus tan 19 degrees. Lo and behold, we've got 1x now. Remember, when we were doing that, one way to get two of the same variable together is look to try and factorise it. Make it so that's a common factor. Now what we can do is divide through by all of this bit. And lo and behold, we got x on its own, because x is this side, 120 tan 19 degrees, over all of that bit in brackets. Tan 47 degrees minus tan 19 degrees. Bang that in your calculator and find x. No, however, equals 56 point what? 75 units meters. Okay, so that distance x is 56.75 meters. Put that on our diagram. 56.75 meters. Now, how can we find h? We've now got the adjacent side, the angle 47 degrees, and the unknown height h, so we can use the tangent, can't we? Tan 47 no, why can't you tell me why you can't use Pythagoras theorem? Yes, you could. You're thinking you could use the 120 plus that, but we don't know either of the hypotenuse lengths, so we can't. Yeah, we only know one side of both the two triangles, so we're going to use tangent of 47 is equal to the opposite side, h, over 56.75. Therefore, h is equal to 56.75 times tan 47 degrees equals, and plug that in the calculator, see what you get. You say that with absolutely no confidence whatsoever, Paul, but that's correct. Alright? Now you've got your calculator in degrees instead of radians, we're winning, aren't we? Alright, so please don't make that mistake in the exam, will you? The reminder is that you've got your angle in either degrees or radians.
60 in radians.
Yeah. So, that's a typical problem around the use of trigonometry and right angle triangles. And it goes back to us doing the factorisation and the rearranging of formulas. You need to be conversant with it. I think I just proven that. Okay? So, moving on, because some people wanted to solve that problem without right angle triangle theory, and we can if we knew the sine and cosine rules for non-right angle triangles. So, if we've got a triangle ABC labelled up in the standard way with the sides opposite the angles using lowercase letter the same as that of the angle, the sine rule says that the side A of a sine A is equal to the side B of a sine B is equal to the side C over sine C. So that rule can be used if we know either one side and any two angles, or two sides and an angle but not the included angle. So if we're talking about the sides A and B here, the included angle is C, and if we knew those two sides and that angle, we wouldn't be able to use the sine rule. Because if what we do here is we take any pair of these ratios and we need to know either both the sides and one of the angles, or both of the angles and one of the sides, to use it to find the unknown. The cosine rule, there's three versions of it, to find, and usually expressed in the square of the sides. A squared is b squared plus c squared minus 2bc times the cosine of the angle A. Notice that the angle there is always associated with the side you're looking for. So a squared and the angle A, b squared and the angle B, c squared, and we're talking about the cosine of the angle C. Sine and cosine rule are likely to be given to you. Just know how to use them and rearrange them. Okay? You can use that rule if you know two sides and the included angle, like that, B and A and the included angle C, or if you know all three sides, then you can find an angle. Yeah? So in combination, these two rules will allow you to solve any triangle, be it right angle or non-right angle. Having said that, to me there seems little point in using these complex rules to find unknowns in right angle triangles. You might as well use the easier trigonometry. The Pythagoras theorem. Also, gentlemen, we can find the area of any triangle in one of three ways. If we know the perpendicular height, here, for instance, we can use half times the base times the perpendicular height to find the area. Or we can use half AB sine C, half AC sine B, or half BC sine A. Or we can use that extra formula down there where we calculate if we know all three sides, we calculate the perimeter, the distance all the way round, and divide it by 2, and then plug that subsidiary variable s into that formula there, and we can find the area. So there's 3 ways you can find the area of a non-right angle triangle, like that. Okay? So, in the triangle XYZ, angle X equals 51 degrees, angle Y equals 67 degrees, and the distance YZ 15.2 centimeters. Solve the triangle, i.e. find all the angles and all the sides, and find its area. So we need to know the angle Z, the side Y, the side Z, and the area. What's the first and easiest thing to find? Yeah. Z is equal to 180 minus 51 plus 67. Which equals, gents, 62. First bit solved. Okay? I'd be happy and confident you could use that in any other calculation because it's not been rounded at all. That's an integer value, it's an exact value, so you haven't got to think about not using that angle in any other formulae. So what can we find next? How could we find the side Y? Sine rule? Yeah. We can go Y over sine Y is equal to we wouldn't use the angle Z here because we don't know the side Z either. So we're going to have to use the side X of a sine X. Yeah? So we're choosing the two versions of the sine formula ratios that will help us to solve this problem. Yeah? Now we've got to rearrange that so it says Y equals something. What do I do? Multiply by, yeah, so, and that's the angle Y, yeah? So multiply by sine Y. Now we can put the numbers in. X is 15.2 times the sine of the angle Y, 67 degrees, all divided by the sine of the angle X, which is 51 degrees. Plug that in your calculator and you should get a result. Answer to that is 18.0, exactly 18. Is it exact, Paul, or are there some decimal places off? Okay, yeah. Then lots of nines. Yeah. That's fine. 18 there. Okay. So we now know the side Y. It's 18 centimetres. What are we going to use to find the side Z? Why can't we use Pythagoras' theorem? Not right angle. Yep. We could go down the route of finding the perpendicular height and making a right angle triangle, but what's the point? That would be a lot of work, wouldn't it? We need the side Z. Yep, you can do exactly the same, but Z of a sine Z is, and which other two would we use? Probably the two we were given, X of a sine X. So do that. Rearrange that. Could you what, Paul, did you say?
If you not put into the original calculation of this topic, we've just got 18 centimetres. Could you not just exchange the 15.2 18?
No, because that's associated with a different angle. The 18 is a different side.
So, 18 times sin 62.
Yeah, you could use the side Y and the angle Y. You could do. You'd still get the same. You should still get the same answer. Well. You still got to rearrange it because you want to find Z this time, and not. You got to start again really because you're trying to find something different, aren't you? You now got to include Z in it, so you got to rearrange that for Z. All done. So the rearranged formula is Z is equal to X sine Z over sine X. And that is X is 15.2 into times sine 67. Oh no, sine of Z, yeah, sorry. 62 now. And the answer is centimetres. Okay? So how can we find the area here? Can we find the area using the initial information given? Just go back to our formulae and look at these ones here. Half BC sine A, half AC sine B. So two sides and an angle that is that is included. Look like it. You've been given one side and two angles. One side and two angles. No, you can't do it. You can't do that with just given information, unfortunately. Let's have a look how he's done it. He's used equals half of xy times the sine of z. Looks like it. So how does that reflect on information given? X was given, Y wasn't, but that was an exact value rather than anything, or more or less exact. You didn't round that very much, Paul, did you? Because that was 0.4999 added on the end, so it hasn't been rounded very much. It has used the angle Z, which is an exact value as well anyway. And all I'm saying is, if you can avoid using calculated values, do so. If you can't, then you just have to go ahead anyway. So that is a half times x, which was 15.2, times y, 18, times the sine of z, which was 62 degrees, wasn't it? Plug that in your calculator and you should get a result. $120 point, yeah, I'll round that to 0.8. 4 significant figures. 120.8 centimetres. So again, that's breaking the problem down. How can we find things as we go along to solve the whole triangle? Yeah? Yeah. Centimetres squared. I put down what somebody said. Okay, so we'll pause